So thanks, Mr. Chair. Good morning, everyone. I had proposed a while ago to give this talk on the use of RCA and the potential to develop alkali-silica reaction. But because of the discussions we are having in the committee 555, in my committee 221, and I would like to give a little bit broader fashion. So we're going to talk about ASR indeed, but towards the end of the presentation. So I think this introduction part is very important, that everybody knows we need to decrease carbon footprint. And we have several different ways of trying to do that. One of the ways is definitely to using recycled concrete aggregates. So I think whenever we talk about recycled concrete aggregates, we need to be a little bit more thorough in and mention whether we are using construction demolition waste or returned concrete. There are completely different types of materials that may be generated out of those. So if we do not distinguish those, it's very difficult to make averages and comparing apples to pineapples, right? So in Canada, we cannot use that for structural purposes and for exposed members. And those are, there is an annex O, which tells that, you know, we need to pay attention on durability features, on the workability and so on. But based on my past experience and other colleagues doing research in the team, I would say that we have basically two problems with RCA nowadays. First is fresh state. Normally mixtures could be super dry, could be difficult to be placed, the rheology is not great, and so on. And secondly, and most importantly, is the durability long-term behavior. We are still not sure how that material will perform in the field over the years, right? Strength is important, as civil engineers we all need, but we can somehow control, especially for conventional strengths. In that perspective, I think it's very important, and try to connect that to the presentations that were done before, is that if you crush a particle, your particle is going to be somewhat like this. So recycled concrete aggregates are not at all whatsoever like original virgin aggregate. So if you want to get the same or similar performance of your recycled concrete aggregate mixture, we need to account for those differences, because otherwise you're going to lose performance, right? Of course, you may have, and this value is very significant. If you have ever tested the residual mortar content value, it may range from 20% to 60% of your particle. So it could be more than half of your particle just mortar, right? So we're going to have higher porosity, lower specific gravity, higher absorption, and so on. So of course, what you're going to do, it's going to decrease your compressive strength, your stiffness in general, and your durability. And then what you're going to do, you're going to put more cement, trying to come up with all of the things, and then you're going to conclude that is not really sustainable, right? Why? Because the mixed proportion is not there. So if you look at the particles, we have cast some concrete with white cement, just to really highlight how is a particle after being completely crushed. And you're going to see that this is very different from the other one. So you cannot, it's like whenever we do proportioning of natural aggregates, you cannot proportion the same way if you're dealing with a limestone versus a granite versus a basalt. All of the features need to get into the mixed proportioning. This is the same thing for the RCA. And this is not new. So in the early 2000s, there has been lots of methods that were developed to try to account for the amount of old mortar in the system. So if you have a conventional concrete, you would have water, cement, sand, and coarse. But if you want your recycled mixtures to match the performance of this guy, you need to account that volumetrically. So two methods of mixed proportioning were created in the early 2000s to tackle that. The first is the equivalent volume, in which the concept is you match cement paste and you match aggregates. And the second one is called EMV, equivalent mortar volume method. In basically what you do, you match the mortar and the coarse aggregates. And even more recently, people are using with particle packing models. So you're going to pack in such a way that your aggregate interlock improves. And aggregate interlocking improvement means improving performance. And then, of course, since you're measuring the residual mortar content you have in your particles, what you can do, you can remove cement and replace it to fillers, for instance, limestone fillers or fillers of other kind. And then you keep the amount of cement very low. And of course, if you are more interested in proportioning techniques, then you can start measuring the distance between the particles so that you ensure that you have rheology, which is one of the big problems of the use of RCA. So this is a published paper that I got with one of my students. So you see, I think the presentation so far, people were using the so-called direct replacement method, which is this guy. So electrical resistivity, if you do a particle packing model versus a equivalent volume, for instance, a matching volume versus a direct replacement, you see how you are losing performance if you simply take your aggregate and use it as is. Same thing for compressive strength. If you do a particle packing compared to a matching volumetrically or a direct replacement. So definitely getting your particle over a cycle and use it as is not the way to go, right? This is another project that I've developed with another student in which we have got some RCA, very deteriorated with limestone and so on, and you can see that with a good proportion we may achieve 60 megapascal with particle packing model. So again, this can be done, and then if you go for direct replacement, which is this guy, you're gonna have a huge decrease of strength. So yes, the quality of the aggregate is very important, but for the RCA is even more complicated because it's not only the quality of your original virgin aggregate, but it's actually the coupling of the quality of that original virgin aggregate with the quality of the cement paste that is attached to that when compared to the new cement paste that you are adding. And stiffness is also a possibility to keep a very good stiffness as well if you account for the residual mortar. So then we decided to do, okay, strength-wise, looks like it works. So let's try to do some durability studies to see whether this concrete could be of interest. So first of all, we have done freeze-thaw. And again, freeze-thaw is the amount of the residual. This plot means the residual dynamic, so it needs to be above and beyond this threshold here. And you see that all of the mixtures with direct replacement, they fail. But if you proportion it properly, the same concrete with that same aggregate, but just take into account, a proportion in a better way, you can get a concrete. So the message here is at some point we need to stop blaming the aggregate we receive. We have an aggregate, yes, it's recycled, it presents more cracks, some initial features, yes. But as engineers, we can proportion that properly to make the concrete to present good performance, right? Now, to cover the topic then of my title here, I just would like to talk about the coupling of recycled concrete aggregate and the possibility of developing further alkali-silica reaction. So as everybody knows here, alkali-silica reaction or alkali-aggregate reaction is a very important durability related topic. In Canada, in the US, worldwide, we just got every 4 years we have a very important conference that was hosted by us in Ottawa in last May. And we know that the cement stable mineral phases of the aggregates we use, with the cement, we develop a gel. The gel itself is not a big issue. The problem is that whenever that gel uptakes water, it induces a swelling and deterioration. So these are some of the photos of infrastructure in Canada and in Brazil as well, affected by alkali-aggregate reaction. So the question we may have is that what is the durability performance regarding AAR from a perspective of a recycled concrete aggregate? So is there any potential for secondary induced expansion, meaning that you have a structure there, it's swollen many years, now you're going to demolish that, you're going to crush it and reuse it again, and what about the deterioration? If it happens to swell again, is the deterioration going to be similar or not? And if there is a possibility of secondary deterioration and expansion, how to prevent it? So I'll just show a couple of results of our past research. So this is an overpass called Robert Bourassa Charret in Quebec City that was demolished after 60 years in service, bearing lots of alkali-aggregate reaction. And the amount of expansion was already above and beyond what we would have expected testing that aggregate in the laboratory. So nevertheless, we crushed it and we decided to cast some concrete specimens out of it, and then it kept, we kept having very important expansion. So yes, it looks like it's indeed there is indeed a very important risk of reusing aggregate as a recycled concrete aggregate bearing alkali-aggregate reactive minerals. So we need to take into account whenever we do a new concrete. It's not because it have deteriorated a lot that it doesn't have potential to keep on going. After those results, I decided to do with other students a little bit more systematic study in which we have done, well, let's try to generate what we call returned concrete in the lab and construction demolition waste. What does that mean? It means that let's get 2 aggregates that are very reactive, one coarse aggregate from Canada and one sand that is very reactive from the region of Texas here in the US. And then let's slightly deteriorated concrete, which would simulate in quotes a returned concrete. So 0.05% expansion just slightly cracks in the concrete. But let's try also to provoke what we would call potentially as a construction demolition waste. So we allowed those concrete specimens to swell up until 0.3. 0.3% expansion is expansion that you can see cracks. You can even break your concrete if you hit it hard. So it's very heavy, I would say, degree of expansion due to AAR. And basically what we have done, so we, the first curve here at the top for both plots here, they show the aggregates in a new concrete. How is the swelling if you put that aggregate in new concrete? So you see lots of expansion, 0.3% expansion, here even more, so very extremely reactive aggregates. But if you tackle that, so you break it whenever the initial concrete reached 0.05% expansion, or even more, 0.30, they both continue swelling. And more or less the same kinetics for the recycled aggregates. It's slightly different here towards the end, but so it delays the process using a recycled concrete aggregate with potential for ASR. It delays the process, but indeed we have a problem here. Same thing for the sand. Same thing for the sand. So if we use a sand with presented already slight reactivity in a concrete or very reactivity, the secondary expansion would be very important. Yes, a little bit delayed over time, but indeed there is a potential risk and we need to account for that. And nicely enough, one thing which is very important in the serviceability side of things for us is to check for expansion, but it's also very important to check for cracks. And we try to plot a curve here, crack density, so the number of cracks per square centimeter of the sample as a function of expansion. All of them, they increase over the expansion, which is logic, but in a very different fashion. And I don't have time and I don't want to get that much in detail here, but you see the charts are different from the different samples, meaning coarse aggregate with low initial expansion, coarse aggregate with high initial expansion, sand with low and sand with, with high and with low, and you see that the features of deterioration are different. What does that mean? It means that not only the expansion will be different, but also the deterioration will be also different. Okay, but what does that mean? It means that the impact in mechanical properties of the affected RCA because of ASR would be also different. So we need to check those things and be able to measure that, otherwise you're going to be making a huge mistake in reusing that aggregate without paying attention on potential reactivity. So the question that raises right now is the following. In Canada we have the 27A that states that we can use given amounts of supplementary cementing materials to tackle aggregates that are very reactive, moderately reactive, slowly reactive, and we have the 1778 in the US more or less saying the same, but the reality is that can we follow this table for recycled concrete aggregates? There is very, very few research. Most of the research conducted in the past was conducted with the 1260, the accelerated mortar bar test, which we know that is not really representative. So what we need to do is to really to tackle research in concrete, accounting for residual mortar and using concrete prism tests to see whether and validate the tables that are there for original virgin aggregates. If we are not doing this, using recycled aggregate with potential reactivity, we are doing that in a very blind fashion and we shouldn't go that way. So, conclusion, RCA is definitely different of being garbage. I'm very afraid of sometimes we say, well, the quality of RCA is so low, so I need to increase cement, and because of that, it's no longer a sustainable material. I think we are, as engineers, we are making a mistake in a very important part of the process, which are we mix proportioning that properly, right? Are we taking actions in a mix proportioning perspective? And very important, I think, research to do in the future, find ways to improve fresh state, and also find ways to prevent alkali-silica reaction in ASR, in recycled concrete aggregates bearing reactive minerals. So with that being said, lots of research are yet to be done. And if you have any questions, thank you very much. I will try to take them. Thank you.